Hello everyone, my name is Joanna Balcerzak and I am working in Orange Innovation Networks. I am a reporter of work item related to federated GANA knowledge planes for multi-domain autonomic management and control of slices in 5G end-to-end architecture. This work item is part of ETSI Technical Committee Core Network and Interoperability Testing. I will show you a short presentation about ETSI GANA knowledge planes, driven networking for addressing autonomicity in 5G end-to-end architecture. So first of all, I will start with the terminology. After I will go through the GANA reference model with focus on knowledge plane. After I will talk about implementation, so how to address autonomicity in 5G end-to-end architecture. And finally, I will present you briefly a list of technical specification, technical reports and white papers related to GANA. So let's start. Briefly, I will try to summarize a few definitions to facilitate the understanding of the presented topic. So first we will start with GANA, so a generic autonomic network architecture, which is a conceptual architectural reference model for autonomic network engineering, cognition and self-management. Its purpose is to serve as a blueprint model that prescribes design and operational principles of autonomic decision-making manager components, responsible for performing autonomic and cognitive management, but also adaptive control of resources. GANA includes enablers for autonomicity. Autonomics is also synonymously referred to autonomicity in the literature. Autonomicity, so it's adaptive control of resources and behaviors. A system that operates using control loop is called an autonomic system, and the system property of exhibiting a closed loop or control loops is called autonomicity, and the science of control loops is called autonomics. Autonomic system requires specific capabilities, which include autognostic capabilities like self-discovery, awareness, and analysis, control capabilities on network elements and interfaces, capabilities to define and verify performance and constraints, but also to identify attacks and run defending actions. By the cognition, we can understand learning, analyzing, and reasoning capability used to effect advanced adaptation of behavior or state of an entity for which the capability is being employed. Cognitive algorithms are, for instance, machine learning algorithms. Autonomic systems with cognitive capabilities are systems which determine their behavior in a reactive or proactive manner based on continuous observation of their environment of operation and are characterized by presence of a control loop structure at the heart of their operation. So now let's move to GANA reference model. Current slide presents a snapshot of the generic autonomic network architecture reference model. This model for autonomic networking, cognitive networking, and self-management is fully specified in the ETSI standard. The aspects of autonomic networking, cognitive networking, and self-management of networks and services are covered in GANA collectively as the autonomic management and control paradigm. Autonomic management and control is about decision-making elements as autonomic functions, logics that dynamically configure the associated managed entities in respective closed control loops, with cognition introduced in the management plane as well as in the control plane. The GANA reference model as autonomic management and control architectural model defines generic functional blocks and the associated reference points and characteristic information, so messages conveyed through those reference points. The key components of GANA knowledge plane are the network decision entities, which are elements that, given the input disseminated from the automated management layer, autonomously take decisions for self-configuration, self-healing, self-diagnosis of the network layer. Various types of GANA knowledge planes, decision elements, can be designed to perform autonomic management and control operations on various types of managed entities in the network infrastructure network elements, virtualized or physical one. Decision elements are representative of cognitive management and control domains of reasoning regarding specific management and control aspects. For instance, it can be fault management, resilience and survivability, auto-configuration, auto-discovery, quality of service and quality of experience and performance management, security management, monitoring, routing management, decision elements can be designed in the knowledge plane. We have three key functional blocks of GANA knowledge plane. So it is GANA network level decision elements. So this decision-making elements whose scope of input is network-wide in implementing slower control loops that perform policy control of lower-level GANA decision elements for fast control loops, instantiated in network nodes. The network level decision elements are meant to be designed to operate the outer closed control loops based on network-wide views or state as input to the decision elements algorithms and logics for autonomic management and control. So the macro level autonomics. The network level decision elements, so knowledge plane decision elements, can design to run as a micro service. Another functional block is overlay network for information exchange. In a distributed scalable overlay system of federated information servers. So the ONIX is useful for enabling auto-discovery of information resources of an autonomic network via publish, subscribe, query, and find mechanism. Decision elements can make use of ONIX to discover information and entities in the network to enhance their decision-making capability. So ONX itself does not have network management and control decision logic, as decision elements are the ones that exhibit decision logic for autonomic management control. And another element is a model-based translation service, which is an intermediation layer between the GANA knowledge plane decision elements and the network elements, which can be physical or virtual. So this layer is for translating technology specific and also for vendor specific raw data into a common data model for use by network level decision elements based on accepted and shared information data model. GANA defines four basic hierarchical control loops levels of abstractions at which autonomicity by associated decision elements may be introduced within the network. So it is protocol level, functional level, node level, and network level called the GANA knowledge plane. So here the key message is that GANA model can be implemented step by step in order to incrementally introduce or implement autonomicity in a networked system and the whole network. Current slide presents the integration of the GANA knowledge plane with various management and control systems through which the knowledge plane can selectively program the network, and there is as well an integration with event sources, data sources, and knowledge sources. The key message here is that GANA knowledge plane enables advanced management and core control intelligence at the element management, network management, and operation and support system level by interworking with them or enhancing and evolving the intelligence of the system at this level by way of replaceable and reloadable autonomics modules that can be loaded at specific abstraction level of management and control operations. From an architecture perspective, a control loop can be based on distributed model for fast control loops. In this case, the decision element is embedded in the nodes, virtual or physical, whereas in a centralized model for slow control loops, the decision element is implemented outside of the network nodes. Both kinds of control loops act towards a global goal to ensure a stable state of the network. Decision elements can negotiate with another decision elements to realize dynamic adaptation of network resources and parameters or services via reference points. Control loops implemented at knowledge plane level are slower than the control loops that may be implemented at NMS, EMS, and network function or network elements level, as the knowledge plane is expected to view the lower level as data sources. For instance, event sources and also policy control and lower level control loops introduced at the lower levels. GANA knowledge plane platform enrich the control plane and the management plane as illustrated on the current slide by the integration of GANA knowledge plane with other management and control systems such as SDN controller, orchestrator, OSS, BSS, Manostacks, etc. In case of 5G architecture, functions such as the network data analytics function and the management data analytics function should be integrated with the knowledge plane platform, so that knowledge plane decision elements can use events and key performance indicators data from the functions in the autonomic operations. Decision elements should dynamically request on demand for the analytic services to be performed by the management data analytics function and or network data analytics function only when the services are needed in order to avoid loading the network with unnecessary traffic monitoring. The monitoring decision element should identify the situation when the analytic services of the management data analytics function and or network data analytics function should be requested for and for which period of time are the analytic services required by the decision elements. So either continuously, periodically, or starting at specific time and for a certain duration of time. The autonomicity capabilities are introduced in the management architecture thanks to autonomic functions, which include the decision-making element at the different layers. This implementation of these autonomic functions in the autonomic network architecture is to be driven by operators' policy of network and service operation as summarized on the current slide. So distributed manner, fast control loops, the autonomic functions are embedded in the network elements, network functions only. EMS, centralized manner, control loops slower than the fast control loop implemented at network element, network function level. The autonomic function are embedded in the legacy EMS. NMS, centralized manner control loop slower than a control loop implemented at EMS level. So the autonomic function are embedded in operators legacy OSS. Now I will talk about more about GANA implementation. So a current slide depicts a simplified view of architecture coming from European project called Slicenet. This architecture, more information about this architecture you can find in, for the moment, it's a draft ETSI TR 103 747, but this technical report will be published very soon. Here we can see only showcasing the relevant components which illustrate how the multiple cognition plane components as well as the monitoring plane are mapped to GANA architecture. More specifically to its knowledge plane and related components. Slicenet cognition plane match the functionality of GANA knowledge plane, as both implement an entity in which reasoning, learning, and adaptation procedures take place in order to govern another entity which focus on the efficient implementation and automation of configuration and provisioning workflows. Both a Slicenet cognition plane and GANA knowledge plane need to be fed by copious amounts of data in order to execute the functionalities related to learning and reasoning. In this regard, Slicenet Data Lake is employed to enable the sharing of information across multiple modules of the cognition plane and across layers. The data lake instance centralizes the monitoring information coming from the monitoring plane, which keeps track of relevant key performance indicators, metrics, and alerts related to the health and performance of deployed network slices. Such approach perfectly matched the information knowledge sharing system defined in GANA, as the main purposes of this framework also relates to the sharing of data between layers and components of the knowledge plane. The key components of GANA knowledge plane are the network decision entities, which are elements that, given the input disseminated from the automated management layer, autonomously take decision for self-configuration, self-healing, self-diagnosis, etc. of the network layer. In this regard, Slicenet also has defined decision elements inside the architecture of its cognition plane. It is the quality of experience optimizer and the rule engine, which are distributed between the multiple roles of the Slicenet architecture. In GANA, both nomenclature, both quality of experience optimizer and rule engine, implement network level quality of service decision elements dedicated to functions to govern operations for quality of service management and control of the network. Both modules receive information from the information sharing system and, according to them, contact the governance system to enforce operations to maintain optimal quality of service level. More specifically, the rule engine is focused on fault performance and optimization enforcement, while the quality of experience optimizer purpose is the maintenance of end-to-end quality of experience level for the deployed network slice for which it is responsible for. Both entities are governed through policies distributed from a policy administrator. These policies indicate under what circumstance what action should be enforced towards the governed system in order to maintain overall optimal quality level. In this regard, Slicenet Policy Administrator implements GANA Policy Control, which is a system based on policies that establishes the rules under which the multiple network level decision elements should behave when interacting with the governed system. Both Slicenet and GANA follow a policy-based approach that rather than an imperative approach follows a more declarative methodology in which the policies and the decision elements specify when and what of the actions of the governance system, while the how it's left to the discretion of the governed system. To enable the interaction between these decision elements and the governed system, Slicenet has defined an interface between the quality of experience optimizer and rule engine and the orchestrator at their level. This interface allows for them to express what is required action to be executed and the essential parameters for the action. It can be increase of bandwidth and so on. While the exact workflow and operations to materialize the action is executed by the orchestrator. This type of interface implements the model-based translation service of GANA architecture, as they serve similar purposes. The MBTS in GANA is a service that allows the multiple decision elements to interact with the automated management system without the need to know the low-level network details of the carried operations, since these are treated by the underlying orchestration and control planes. As such, both Slicenet and GANA follow an agnostic approach for the communication of the decision elements and the governance system, simplifying the exchange of operations between the two groups of entities. Aside from this, quality of service network level decision elements, Slicenet also defines other entities that may act as network level decision elements. This is the case of the machine learning models execute within the analyzer at the cognition plane. These modules act as advanced monitoring and sensing function of the underlying network system and deployed slices, extracting data from the shared data lake and inserting back elaborated events that provide insights about their status. These elaborated events may then be used to trigger the quality of service network level decision elements, while machine learning model don't machine learning models don't execute any kind of decision in regard of configuration of the network of slices. They produce valuable information which can influence on the behavior of quality of experience, quality of service related configuration operations. So the multiple machine learning models defined in Slicenet can be understood as other network level decision elements in GANA nomenclature, since they don't fall into a classic network level category such as quality of experience or routing, but contribute towards the general decision making of the cognition subplane knowledge plane. There is a need for introduction of autonomic management and control in the overall end-to-end 5G network architecture. It's a framework in which an underlying network infrastructure layer is governed by another entity that provides insight about the overall system and then enforce actions to the infrastructure layer. When we look at the figure on the current slide, so on the right, first, an automated management layer in which reasoning, learning, and adaptation procedures take place. Then the created insights are distributed to autonomic management and control layer, which focus on the efficient implementation and automation of configuration and monitoring workflows. The key elements of the autonomic management and control layer are the GANA knowledge plane. decision elements, which given the inputs disseminated from the automated management layer, it can be policies, for example, autonomously take decision for self-configuration, self-healing, etc. of the network layer. Lastly, a common knowledge base is present for the sharing of data between the layers. Slicenet Cognition Plane combines both layers' capabilities in which insights are gained through specialized analytical functions. Overall behaviors are defined thanks to policies and configurations that are determined through the capabilities of dedicated decision elements, namely the quality of experience optimizer. Machine learning provides an algorithmic approach for autonomic management and control to learn, adapt, and improve continuously based on feedback control loop. Machine learning is a pivotal technology with autonomic management and control, where the end-to-end system behavior is adjusted in response to a perception of the end-to-end system environment and the proceed information, experience, and intelligence within the knowledge plane. In this example, Slicenet cognitive plane also uses machine learning techniques to derive the operational aspects for services, network slices, and underlying network infrastructure resources. Integration of machine learning techniques into end-to-end network slice management and orchestration is essential to achieve an autonomous closed control loop network. So just to summarize, the first step in the instantiation of GANA onto an implementation-oriented reference network architecture and its management and control architecture is to define the decision elements needed for each function of network elements that may be managed and the associated types of managed entity for specific use cases. The result of the instantiation is autonomicity, so an autonomics-enabled reference network architecture and its management and control architecture with definitions of the autonomic function that should be implemented in network elements and in the knowledge plane, as well as the mapping of the decision elements to manage entity. They should autonomically orchestrate, manage, and control by applying algorithm that dynamically orchestrate or configure manage entity and a configurable and controllable parameter in response to various types of changes such as workload changes, policy changes, manifestation of faults, errors, failures. So now I will present you briefly a list of technical specification, technical reports, and white papers related to GANA. So ETSI TS 103-195 Part 2 defines an intelligent management and control function block called GANA knowledge plane that is an integral part of management and control system for the network. It specifies APIs that should enable to integrate ETSI GANA knowledge plane, SDN, NFV, and end-to-end orchestration, big data driven analytics for AMC and OSS-BSS system. All technical reports from current slide provide the answer to the question of how implement GANA defined autonomic manager components called autonomic functions that implement control loops in physical network elements and functions and in virtualized network functions, VNFs. In ETSI INT, you can find as well proof of concept program on 5G network slices. And here there is a list of white papers from this proof of concept program. Thank you for your attention.